Lancaster University offer holder day. Let's go. So we got to the hotel and there was a dog on the bed. His name was Sam. I did not get to take him home. But check out this hotel room. Very cool. I liked it a lot. And Lancaster's famous for two things, obviously the War of the Roses and the plane. Roses absolutely everywhere. This is the only place that I saw the plane. So this got a photograph. And for staying at the hotel, I got some sunflower seeds. And I love flowers, so that was beautiful. Oh yeah, and the hotel also had fish. Now, onto the university, which, by the way, was only across the street from our hotel. We found this cool drawer of maps in the library. Also found this very cool acrylic painting in the library. It's massive, by the way. It's like the size of the whole wall. Then we found the actual chemistry part of the library, but there were no books on disasters this time, so, slightly disappointed, really. Then, as always, chemistry hospitality rules supreme. I ate far too much of this. It wasn't healthy. And then I found the dry ice delivery bucket. I've not seen this anywhere else, and I mean, it makes sense, but it's a bit odd that it's there. They also have a chemistry piano, so I mean, swings and roundabouts, am I right? Also got a lot of free stuff. A book, a second book, a pen, a second pen, a reusable hand warmer, very useful, and a very cool notepad. Oh, and the bag itself, obviously. So, on to the actual lecture. We did expediting drug discovery with metal catalysis. And it started with the question, what do you think is the most profitable drug? So I want you to take a second and think about your answer to that. Okay, time's up. You might have said paracetamol. Or maybe you said aspirin. Or maybe cocaine, if we're talking about non-pharmaceuticals. And I said paracetamol. The answer is Lipitor. Now, if you're anything like me, I had no idea what Lipitor is. It was the first ever statin, which helps with coronary heart disease, and it's earned £131 billion in its lifetime. A blockbuster drug is any drug that earns over £1 billion in profit. £1 billion is a lot of money for what most drugs are made of. So what do you think they're made of? Unless you said 98% chalk, cellulose, emulsifiers and thickeners and only 2% the crucial molecule, you're unfortunately wrong. And 90% of these critical molecules are small organic molecules. So cimetidine, which is marketed as Tagamet, is a heartburn medication and it was the world's first blockbuster drug. Or this one, which is fluoxetine, or marketed as Prozac, which is an antidepressant. Or clopidogrel, which is marketed as Plavix, which is a blood thinner. And then there's sildenafil, which is marketed as Viagra, which is used to cure... So what makes good drugs? Well, good drugs are potent and selective. It's called pharmacodynamics, and what that means is just the effect of the drug in the body. Because obviously you want it to cure whatever you have, but you don't want it to give you horrible side effects. And you want it to be potent because you don't want to take a kilogram of drugs every day. And then the other word is pharmacokinetics, and this is the effect of the body on the drug. So obviously you want it to be absorbed and distributed correctly, and you want it to exit the body at about the right time. You want a cancer drug to stay there for a couple of days, maybe a week if you're lucky, but if you had a sleeping pill that lasted that long, you'd be concerned. So all of these specifics mean that it can take up to 15 years to develop a drug, and that's partly why they're so expensive, because they've got to burn through tens of thousands of selections of organic materials to end up with one. Catalysis can make this process much greener and much cheaper. And it's all about finding the exact correct metal catalyst for this one organic molecule that you found, and sometimes it's enantiomer. It really depends on the drug itself. Something I learned from this is even if you're making only one enantiomer for your drug, you have to specify and test what the other enantiomer does, because obviously if it's too dangerous and too great a risk, then they won't let you sell it. Then we went into tutorial sessions and we learned about transition metals, and we spoke about Werner, who created the nomenclature for transition metals, and Dorothy Hodgkin, who discovered that cobalt was at the center of B12. And we discussed different ligands and what they did, and he did a demonstration with some of them by adding them to the transition metals, except for pyridine, which he said apparently makes you sterile. So the question is, how can you create different catalysts with different combinations of ligands and transition metals? So, on to the practical bit. We used tetrachloroaurate and we heated and we stirred it. Then you add sodium citrate and you keep heating and stirring it, and you note the colour changes. My favourite on this list is Ribena purple, because describing colours is really difficult. So red is the smallest nanoparticles, whereas blue, or colourless as I've put it, is the larger ones. So what does that tell us? Well, it tells us that in this heating and stirring, the nanoparticles are actually shrinking. And that suggests that different sizes of particles absorb different wavelengths, and that's really interesting. Then we took a red dye solution and we compared it to our gold nanoparticles, which, like I said, were red at this point. Now, I didn't take a photo of this, but what we did is we shone a laser through the gold nanoparticle solution and through the red dye, and the difference is, in the gold nanoparticle solution, there's a thin kind of beam all the way through, whereas in the dye it kind of glowed. Next, we took our gold nanoparticle solution and we added 0.2 molar salt solution and 2.5 parts per million melamine solution, and both of the solutions turned blue, but the melamine was significantly slower. Now, if you pass the gold nanoparticle solution through a 0.2 micrometer syringe filter, it will come out the other end. So that tells us that the nanoparticles are less than 0.2 micrometers. But with either of your gold solutions with salt or melamine added, it's greater than 0.2 micrometers, so it doesn't fit through the filter. Now, which is the strongest coagulant? Well, it's not actually salt, despite the fact that salt produced faster results. The thing you need to remember is that the melamine solution was 2.5 parts per million, so it was so much less concentrated than the salt. But melamine is a greater coagulant than salt because it contains more lone pairs, so it can bond to more gold atoms. And this was it, our final result. As you can see, that little yellow line across the top is our gold film of nanoparticles. Very cool, but no, I didn't get to keep it. And that's going to be it. Thank you so much for watching. Please remember to like and subscribe. I really hope you enjoyed. And that's going to be it from me for about a month or so, because I'm going into A-levels. But I'll see you on the other side. Thanks again. Bye.